Hello, it's me, Ivan Aviles, again. So we are going to see again a chapter of Kreizsig book. In this case is chapter 11, module 1 for 3. The chapter number 11 is talk about partial differential equations. Or PDEs. The partial differential equations is an equation that has one or more partial derivatives of an unknown function. It's like the same like ODEs, but in this case it's with a partial differential equations. Exists a lot of cases like the head equations, the Laplace equations. All of these kind of equations is an partial differential equations. Okay, so for what are the applications of the PDEs? The applications are in the quantum mechanics, quantum physics, also in electromagnetism, in the flow, etc. So for this are very important to know how to find the, in this case, the unknown function of the partial differential equation. So let me see. We are going to see the basic concept of the PDH. So in this case, the function that we are going to find is the function u. Okay? So in this case, it's a if you it's the same. If you have a first order partial differential equation, is a first. Oh yeah, it's a first. It's a linear partial differential equation. And if you have, or I don't know, second order, third order, fourth order, these ones are, or those ones are for non-linear equations. Okay? So we are going to see an example. Find the solutions of ux minus u equals 0. Okay? So in this case, we want to find in x, in the plane xy. So first we only have this, that this is the same as we know this, equals 0. So as in the previous courses of solve a differential equation, you can see that u is equals to a to the power of x plus b to a 2 equals 0. Yeah? No, sorry. So, why? Okay, so we are going to know why. We have this formula. This is plus a plus by equals 0. So also have that y is equals, in this case we find the solution because a squared minus 4b is less from 0, because in this case a is equals 0 and b is equals 1. So minus 4 is less for 0. So we are going to apply this case that says that y is equals to a to the power of minus ax over 2 to a cosine of omega x plus b sine of omega x. That omega is equals to the square root of b minus 1/4 of a squared. Okay, in this case, this equals to b, that b is 1, that is 1. Okay, so we don't have problems. We substitute the values, we find these values. Okay? I'm sorry. So this is the answer. Okay? So, but we want to in terms of x and y. And for this are I of y ex plus b of y e minus x. So this is the real answer. Okay? I'm going to erase that. And I am going to check the module 2 of the chapter 12, that is modeling. Let me see. Modeling, vibrating a string. So we are going to solve this kind of equation that also solve in the wave equation. Okay? So let's imagine that we have this kind of graph that is u. Let me check. L. We have this one, we have this, and this, P and Q endpoints, and we have this T tension, T1 alpha, T2 beta. Okay? So this is x plus delta x. So we have two tensions. Sorry. We have two tensions in two endpoints in a small area or small portion of the string. Okay? So for this, we have that the component of x are equal to t1 cosine of x equals t2 cosine of x. No, it's not cosine of x, sorry. It's cosine of alpha, cosine of beta equals t. Okay? So, in the vertical or in the components of u, we have that is minus, because we have this, minus t1 sine of alpha, and the other component are t2 sine of beta. Okay? So, like the Newton's second law said, the resultant is, in this case, P delta x times the second order differential equation of u by respect of t. Okay? So, like as we said, this is equal to this rho. Okay? So in this case, we are going to divide by these ones, and we have that this is equal to, let me see, yeah, T2 cosine of beta, T1 cosine of alpha, and all of these this one and this one are tangent of beta minus tangent of alpha, that is equals to rho delta x over t for this one. Okay? So this is one equation, and let me see if I can erase. Yeah, I'm going to erase. Okay, so let me see, tangent of alpha is equals to the first derivative of respect of x over x, that is at this point, and tangent of beta is equals this one, but respect of x plus delta x. Okay? So if we substitute in here, we have 1 over delta x. If we pass this for this, and we substitute in here, so we have this one, u x plus delta x minus first derivative of respect of x, that is equals to this rho over t times the second derivative of u by respect of x squared. Okay? So for this one, I'm going to erase this. So I am going to write here. So if delta x is equal to 0, we have this equation to be seen. That c squared is equal to t over rho. Okay? we are going to see the next model, that is the solution of by separating variables use a Fourier series, okay? In one way, that is this one, okay? I'm going to write here c squared equals t over rho. Okay. So if we need to have the boundary variables or constants, that in this case is x equals 0 and t equals L. Okay, so here we have the boundaries. So in this case, if we put here is 0, and let me check, L x equals 0. Okay. So, but if we have u x is equal f of x, u0, sorry. Sorry. U of x0 and u of t x0 is equals to g of x. So we have that u of t is equals to the first partial derivative of u by respect of t. Okay? So in this case, if we have u of xt, we have this one, that is f of x times g of x. Okay? So also we have that the second partial derivative of u respect of x, of t, is equals to fg. And also we have the second partial derivative, but in this case respect of x is equals to the second derivative of x times g. Okay, so if we evaluate, so in this case we have fg is equals a constant of c squares times fg. Okay? So in this case, let me see. So for this one we have this. This equation, let me see, case f equals 0 and g minus c squared kg equals 0. Okay, so if g equals 0, u of fg is equals 0. For these four k equals u squared. In this case, it's very interesting. We have this solution that f is equals a e to the power of ux plus b e to the power of u minus ux. So we have for general solution that f of x is equals a cosine of bx plus b sine of bx. That b is equals m pi over l. So for this we also solve the the step 3, that is equals u and u x c equals of the sum n equals 1 to the infinity of u n x t, but this is also equals to the sum of n equals 1 of bn cosine of mt plus bn sine of nt sine of np over lx, that lambda n is equals c m pi over l. Okay, so we are going to solve an example. It's very hot. So first we have this formula. Let me see. U of xt works. Okay, that is equals of 1.5 minus ct plus x plus ct. Okay, so we are going to see the final example. So let me see. We have this example that is f x equals K over L x with 0 x L over 2 and 2k over L minus x 1.5 x L. Okay. So I'm going to solve it. This 2k over L, and I'm going to mark better to see better this 1.5 x L 0 x 1.5 f of x equals. Okay, thank you. So in this case, g of x is equal 0, and b star of x is also equal 0. And for this we have u of x of t that is equals to, as we have in this formula, and if we substitute in this one, so we have 8k over pi, yeah, pi squared, and we have, as we have in this one, is Pn that is equals to this, that is equals to 1 over 1 is to the power of 2 of or squared sine of 1. Let me see, yeah, 1, because it's equals to yeah, to sine pi. So this is equals to sine and pi over L, the formula said, of x cosine of cosine of 1 over L of xt. And also, like this Fourier transform, we have another sum that is minus 1 over 3 sine of 3, that is 3, I suppose, yeah, 3 pi over L for this formula. And as we said, we don't have this b star, so we have 3 pi over L cosine of, in this case, is 3 over L xt. Okay, so this is the answer, this is the final answer of this example. And for this, I finish. So this kind of partial differential equation, if you solve it, you can use to, I don't know, to solve any kind of physics problems, like I said, that quantum mechanics or electromagnetism, or any kind of problems that you have a differential equation or differential partial equation. So for this is very interesting, and for that it's all for me, and I think that is the last video, and thank you very much to saw me, and see you in the next semester, in the next period. So bye, teacher.